Hi everyone, I am pleased to present our work. Active, towards highly transferable 3D physical camouflage for universal and robust vehicle evasion. Active, which stands for adversarial camouflage for transferable and intensive vehicle evasion, is a state-of-the-art physical camouflage framework designed to generate universal and robust adversarial camouflage capable of concealing any 3D vehicle from detectors. Our framework greatly enhances the robustness, universality, and naturalness of adversarial camouflage compared to previous methods. Our main contributions include triplanar mapping within Neural Renderer, which removes UV mapping constraints, making it applicable to any object. Stealth loss, which minimizes the detection scores across classes, rendering the target vehicle undetectable. Naturalness enhancement by larger texture resolution, applying smooth loss, and introducing camouflage loss for better concealment. Our extensive experiments demonstrate that active is superior, providing universal performance across instances, classes, models, tasks, and domains. To train our adversarial texture, we first synthesize the reference, mask, and depth images using the physical simulator. We then extract the masked reference image and compute the projected texture using a triplanar mapping mechanism. Using both inputs, we transform the car's texture using our neural texture renderer. We use multiple vehicles during this process to improve the universality. Next, we extract the background and combine it with the rendered vehicle to get the full adversarial image. We augment the adversarial image using our proposed random output augmentation to enhance the robustness and feed it to the target vehicle detector to compute the attack loss. We called our attack loss stealth loss as we minimize the valid maximum detection score across classes. To increase the smoothness of our texture, we utilize the smooth loss, which minimizes the distance of neighborhood pixels. We also introduce camouflage loss by extracting the dominant colors of the background image and enforcing the texture color to be close to it. By combining and weighting the losses, we compute the total loss and use it to update our adversarial texture via backpropagation. In triplanar mapping, we use depth image and camera parameters to calculate an object's surface normal and surface world coordinates. These inputs are used to compute the triplanar mapped texture. In detail, the surface normal is converted to a triplanar mask to get the dominant surface orientation for each axis. The surface world coordinates are converted to repeated surface coordinates by modulating coordinates with the texture size based on projection augmentation parameters to get a repeated texture effect. We take each axis of the coordinate as the texture's UV and map the adversarial texture using these UV maps. Finally, we apply triplanar masks for each mapped texture and combine it as the final triplanar mapped texture. We developed our neural renderer that builds upon the differentiable transformation network from previous work. Specifically, we discovered that the transformation features in the DTN were redundant. Our neural texture renderer can produce similar results by utilizing only the last TF multiplier and TF final adder. Furthermore, the original DTN was trained with 50 random color textures, which is inefficient. Our experiments confirm that using 9 boundary colors is enough to generalize other random colors in test sets, making our proposal more efficient. After optimizing the adversarial texture, we evaluate its performance by fully rendering it using a physically based simulator and performing extensive evaluation. The texture is optimized to attack YOLO v3 and tested on diverse object detector architecture, including single-stage, two-stage, and transformer-based detectors, to assess its robustness and universality. Moreover, we assess our texture on segmentation models, extending the evaluation to different tasks. Here are attack comparisons between our proposed method and previous works in robustness evaluation. It's clear how our proposal consistently outperforms prior works across different detectors and viewing angles. Here are attack comparisons in our universality evaluation. We thoroughly assess the effectiveness of adversarial camouflage across various target objects, using up-to-date detectors, different tasks, and classes. Once again, our proposal outperforms prior works. Finally, here are the real-world sample evaluations of our adversarial camouflage using practical, real-time detectors. Our experiments confirm the effectiveness of our camouflage in real-world scenarios. Thank you for your attention. For more details, including our paper, demo videos, and additional resources, please visit our project page. We also welcome you to explore our poster at ICCV 2023.